Okay, so now we're going to start section 8.3. 8.3 is essentially doing the same thing, except this time we are not assuming that you know the population standard deviation. That's essentially the only difference between the setups between the problems. So notice that the assumptions here are going to be the same. We still want a simple random sample. We still want the variable that we're measuring to be normally distributed, or we need to be taking a large sample. But notice that 3 here is different. 3 says that sigma is unknown in this case. And the main effect that that's going to have is that instead of using the z distribution for these, because sigma is unknown here, we're going to be using the t distribution. So we'll be using that t table that we've looked at earlier. If you'd like, we can look at it now. Remember that if you look at the distribution pages that I gave you, we have these 2 pages that correspond to the standard normal distribution. There's the negative z-scores, the positive z-scores. The third page here refers to the t distribution. So this is the page that we're going to be using in section 8.3. Now, again, what I'd recommend for this video and for the next one is just that you have these steps in front of you so that you can verify that we're going step by step through this process. And notice that this is also kind of convenient because you can look at what the rules are for accepting or rejecting the null hypothesis. So it might be convenient to just have this in front of you as we go through this video. But essentially everything here is exactly the same as before. There's one subtlety, though, that you need to remember, which is that the t distribution has one extra parameter, which is its degrees of freedom. So remember that here we need to decide the degrees of freedom. The degrees of freedom is always going to be n minus 1, where n is the sample size. So just keep that in mind. We're going to need that in order to find our t-scores or to compute different areas. But essentially, the rest of the procedure will be the same. So let's look at this example. Here it says the mean pH level of 16 randomly selected lakes is 6.7. So these are randomly selected. That's good. At a 5% significance level, does the data provide sufficient evidence to conclude that on average the pH level of all lakes is greater than 6? Assume that the pH level of all lakes is distributed normally and that the standard deviation of this sample is 0.68. Okay, now notice that in this case, we do have a simple random sample, so that's good. We do have that the variable that we're trying to measure, which is the pH level of lakes, is normally distributed. And we do have a standard deviation, but it's the standard deviation of the sample. So in this case, the population standard deviation is unknown. We only have the standard deviation for the sample. So because of these 3 assumptions, we're going to be using this table at the beginning of 8.3 because they match the 3 assumptions here. Essentially, the only difference between this and the previous section is that here, sigma is unknown. So when sigma is not known, you have to be using this t distribution. When sigma is known, you'll be using the z distribution. But otherwise, the strategy is exactly the same. So again, we'll start by writing down these hypotheses. So we want to know whether the pH level of the lakes is greater than 6. So our null hypothesis will just be that the pH level is 6. And the alternative hypothesis, which is what we're trying to test, is whether that pH level is greater than 6. So if you'd like, here's a picture that we have. We know that the assumed mean is going to be 6, and our sample mean is over here at 6.7, which is a little bit to the right. And the question is this far enough over to the right for us to reject the null hypothesis in support of the alternative that the mean is greater than 6? The significance level was just given to us in the prompt. So that's usually going to be true. Usually the prompt will just tell you that there's a certain significance level. If the prompt doesn't say that, then normally we just decide on a significance level that's something like 10, 5, or 1%. Okay, now we'll compute the test statistic. It's the same method of computation. Notice here, though, that we're using the sample standard deviation. But otherwise, it's the same idea. So we'll take the sample mean that we got. It says that the sample mean was 6.7. We're subtracting it from the mean from the null hypothesis, so that would be minus 6. And then we're dividing by the standard deviation for this sample mean picture. And that standard deviation, remember, was sigma divided by the square root of n. So that goes in our denominator. In this case, we have a sample standard deviation of 0.68. And we should divide by the square root of n, where n is our sample size. So that would be divided by the square root of 16. And remember, if you're punching this into a calculator, I would parenthesize the numerator and the denominator just to make sure that the calculator understands what it is that you're computing. If you do that, you should get a 4.11 or a 4.12. So maybe punch that in with your calculator and make sure that you're getting the same answer that I'm getting. But this is what I have so far. And now there are two different approaches that you can take here. Whenever I'm using the t-distribution, I usually prefer to use the critical value approach over the p-value approach, because the p-value approach, remember, was the one that depends on computing this area, the area over here to the right. And computing that area won't necessarily be possible with t-values. You can approximate it, but you can't necessarily compute it exactly. So for that reason, I'm going to recommend that you just stick with the critical value approach here, but I'll show you how to do both of them in case you want to try the p-value approach. So for the critical value approach, what we need to do is we need to find our critical value. That would be t sub alpha, which is t sub 0.05. So we're looking for the t value that has an area of 0.05 to its right. And that would represent our critical t value here. So this will be t sub alpha. And what we'll say is that if our test statistic is to the right of this, then we would reject the null hypothesis. And if our test statistic is to the left of this, then we would accept the null hypothesis. Okay, so let's talk about how to compute this. We want a t value that has 5% area to the right of it. So for this, we're going to use our distribution table. Now remember, our sample size was 16. We sampled 16 lakes. So that means that the number of degrees of freedom that we have here will be 15. So I'm going to be using this row. But now we need to decide which column to use. And remember, what we're looking for is this critical value, t sub 0.05. What that means is that we want an area of 5% over here to the right. And what that means is that for one tail, we want 5% of the area. So that means we're going to be working in this column. And if we look at the intersection here, what we end up getting is this value. This is the t value. So this is t sub 0.05. It will be 1.753. So that tells us the t value that we're working with here. Oops. So what I got as my t value is 1.753. But we also know our test statistic was 4.11. And that is further to the right than 1.753. So in terms of a picture, what we're looking at is we have a cutoff or a critical value of 1.753. And what we found is that our test statistic is over here to the right of it at 4.11. And therefore, because our test statistic lives over here to the right side of our cutoff value, we would reject the null hypothesis. Now, if you wanted to do the p-value approach, you could. What you would be doing is you would take our test statistic, which is 4.11, and you would be trying to find the area to the right of that, because that would tell you the area which corresponds to the probability of getting a test statistic as extreme as ours, if this null hypothesis happened to be true. So we want sort of the odds of getting such an extreme test statistic, sorry. So now let's think about our test statistic here. It was 4.11. Now, the reason that I don't recommend using the p-value approach here is just because in this table, you won't necessarily be able to look up any arbitrary areas. In fact, the only areas that we can get are the areas up in this top row. So we'll only really be able to approximate the area that we have to the right. But the way that we should do that is this. Remember that this section of the table, so the interior of the table, is telling us all of the t values. So I would be looking up a t-value of 4. But I have to stay in this row because I have this fixed number of degrees of freedom. So I would be looking at these values. And what I notice is that these values are increasing as I go over to the right, but they never quite make it to 4. The closest that I can get to 4 is this far right one. And the area to the right of 2.947 is 0.5%. So in other words, whenever you make it over to 2.947 as your t-value, this area over here is 0.5%. But the t-value that we actually wanted to look up in the table was even further to the right. It was a 4.11. So we don't actually know what the area is to the right of 4.11, but we do know that it's less than 0.5%. And that'll be good enough for us. So in this table, whenever you're using the p-values, you won't necessarily be able to look up the exact area that you want, but you can estimate it. So what we'll get is a p-value. There we go. We'll get a p-value that is less than or equal to 0.5%. And in particular, what that means is that our p-value is less than our level of significance, which was 5%. And therefore, the decision rule says because p is less than your significance level, you would reject h naught. So these both come to the same conclusion again. And what we could say as our interpretation is it is unlikely that we would get this test statistic if h naught were true. Because remember, h naught says that we should be getting values near 6. Instead, we were getting values that were further to the right of that as our sample mean. So we reject h naught. And the technical thing to say here is just that because the likelihood of getting such an extreme test statistic is less than 5%, there's only a 5% chance that we would get a test statistic like this if h naught were true. So there's a much higher percentage chance that h naught is false. So we'll reject h naught. And again, in all of these problems, it's possible that h naught is true and we just got really unlucky in our choice of lakes. So maybe we just happened to select 16 high pH lakes. But in this case, this is sort of the best that we can do. Like all that we can do is make an educated guess that we should reject h naught. It's possible that, we just got unlucky and h naught happens to be true, but we have enough evidence that we're